Learning objectives. In this chapter, the user would learn the following in detail: queuing systems, MMSK queues, Burke's theorem, MG1 queues, delay in synchronous and asynchronous time division multiplexing, network of queues, Jackson's theorem, closed queuing networks. Burke's theorem. The analysis of the MMI, MMM, MM infinity, and MMMM systems was based on the equality of the steady-state frequency of transitions from j to j plus 1, that is, pj to pj into j plus 1, with the steady-state frequency of transitions from j plus 1 to j, that is, pj plus 1 to pj plus 1 into j. These relations, called detailed balance equations, are valid for any Markov chain with integer states in which transitions can occur only between neighboring states, that is, from j to j minus 1, j or j plus 1. These Markov chains are called birth-death processes. The detailed balance equations lead to an important property called time reversibility. Consider an irreducible aperiodic discrete time Markov chain xn, xn plus 1, so on, having transition probabilities Pij and stationary distribution Pj, j greater than or equal to 0, with Pj greater than 0 for all j. Suppose that chain is in steady state, that is, Pxn is equal to j is equal to Pj for all n. This occurs if the initial state is chosen according to the stationary distribution and is equivalent to imaging that the process began at time minus infinity. Suppose that we trace the sequence of states going backward in time, that is, starting at some n. Consider the sequence of states xn, xn minus 1. This sequence is itself a Markov as seen by the following calculation, where the third equality follows from the Markov property of the chain xn, xn plus 1. Thus, conditional on the state at time m plus 1, the state at time m is independent of that at times m plus 2, m plus 3. The backward transition probabilities are given by, as shown, if Pij star is equal to Pij for all ij, that is, the transition probabilities of the forward and reverse chain are identical, we say that the chain is time reversible. Properties of the reversed chain. The reversed chain is irreducible, aperiodic, and has the same stationary distribution as the forward chain. The intuitive idea here is that the reversed chain corresponds to the same process looked at in the reverse time direction. Thus, if the steady-state probabilities are viewed as proportions of time, the process visits the states, then the steady-state occupancy distribution of the forward and the reverse chains are equal. If we can find positive numbers pi, I greater than or equal to 0, summing to unity and such that the scalars Pij star is equal to Pj, Pji by Pi, Ij greater than or equal to 0, form a transition probability matrix, that is, sigma j equal to 0 to x, Pij star is equal to 1, I is equal to 0, 1, then Pi, I greater than or equal to 0, is the stationary distribution and Pij star are the transition probabilities of the reversed chain. A chain is time reversible if and only if the detailed balance equations hold Pi Pij is equal to Pj Pji, Ij greater than or equal to 0. This follows from the equality Pi Pij star is equal to Pj Pji and the definition of time reversibility. In other words, a system is time reversible if in a typical system history, transitions from I to j occur with the same frequency as transitions from j to I. Chains corresponding to birth-death processes Pij is equal to 0 if modulus I minus j greater than 1 are time reversible. Shown below is an example of a time reversible chain. By splitting the state space in two subsets as shown, we obtain global balance equations which are identical with the detailed balance equations. Shown below is an example of a chain which is not time reversible. The states in the forward and the reverse systems move in the clockwise and counterclockwise directions respectively. Forward chain, reversed chain. The idea of time reversibility extends in a straightforward manner to irreducible continuous time Markov chains. The corresponding analysis can be carried out either directly or by discretizing time in intervals of length delta, considering the corresponding discrete time chain and passing back to the continuous chain by taking the limit as delta tends to 0. All results regarding the reversed chain carry over almost verbatim from their discrete time counterparts by replacing transition probabilities with transition rates. In particular, if the continuous time chain has transition rates Qij and a stationary distribution Pj j greater than or equal to 0 with Pj greater than 0 for all j, then the reversed chain is a continuous time Markov chain with the same stationary distribution as the forward chain and with transition rates. Qij star is equal to Pj Qji by Pi, Ij greater than or equal to 0. If we can find positive numbers Pi, I greater than or equal to 0, summing to unity and such that the scalars Qij star is equal to Pj Qji by Pi, Ij greater than or equal to 0, satisfy for all I greater than or equal to 0, summation j is equal to 0 to infinity Qij is equal to summation j is equal to 0 to infinity Qij star. Then Pi, I greater than or equal to 0, is the stationary distribution of both the forward and the reversed chain, and Qij are the transition rates of the reversed chain. The forward chain is time reversible if and only if its stationary distribution and transition rates satisfy the detailed balanced equation. Pi Qij is equal to Pj Qji, Ij greater than or equal to 0. Below image shows the forward system number of arrivals, number of departures, and occupancy during closed limit 0 to t. Below image shows the reverse system number of arrivals, number of departures, and occupancy during closed limit 0 to t. Burke's theorem. Example: consider the MMI, MMM, and MM infinity queuing systems. We assume that the initial state is chosen according to the stationary distribution so that the queuing systems are in steady state at all times. The reversed process can be represented by another queuing system where departures correspond to arrivals of the original system and arrivals correspond to departures of the original system, as shown in the previous figure. Because time reversibility holds for all these systems, as discussed above, the forward and reverse systems are statistically indistinguishable in steady state. In particular, by using the fact that the departure process of the forward system corresponds to the arrival process of the reversed system, we obtain the Burke's theorem as discussed next. Consider an MM1, MMM, or MM infinity system with arrival rate lambda. Suppose that the system starts in steady state, then the following hold true. The departure process is Poisson with rate lambda. At each time t, the number of customers in the system is independent of the sequence of departure times prior to t. Proof. This follows from the fact that the forward and reversed systems are statistically indistinguishable in steady state and the departure process in the forward system is the arrival process in the reverse system. For a fixed time t, the departures prior to t in the forward process are also the arrivals after t in the reversed process. The arrival process in the reverse system is independent Poisson, so the future arrival process does not depend on the current number in the system, which in forward system terms means that the past departure process does not depend on the current number in the system. Part B of Burke's theorem is quite counterintuitive. One would expect that a recent stream of closely spaced departures suggests a busy system with a typically large number of customers in queue. Yet, Burke's theorem shows that this is not so. However, that Burke's theorem says nothing about the state of the system before a stream of closely spaced departures. Such a state would tend to have abnormally many customers in queue in accordance with intuition. We say that Qj is a downstream neighbor of Qi if there is a positive probability that a departing customer from Qi will next enter Qj. We say that Qj lies downstream of Qi if there is a sequence of queues starting from I and ending at j such that each queue after I in the sequence is a downstream neighbor of its predecessor. A queuing network is called acyclic if it is impossible to find two queues I and j such that j lies downstream of I and I lies downstream of j. Having an acyclic network is essential for the Poisson character of the arrival and departure processes at each queue to be maintained. Closed queuing networks. Closed queuing network is a network of queues where the total number of customers is fixed because no customers are allowed to arrive or depart. Closed networks can be analyzed using Markov chains, and it can be shown that the steady-state occupancy distribution has a product form under assumptions similar to those used for open networks. For simplicity, assume a single customer class. Let M be the fixed number of customers in the system and let Pij be the routing probability that a customer that departs from the queue I will next visit queue j. Because no customer can exit the system, we have let also mu j of M be the service rate at the jth queue when the number of customers at the queue is M. An important difference from the open network case is that the total arrival rates denoted lambda j of M at the queues j is equal to 1 to k are not easily determined. Consider the equation. By setting to 0 the external arrival rates Rj, we obtain these equations do not have a unique solution anymore, but under some fairly natural assumptions, they determine the arrival rates lambda I of M up to a multiplicative constant. Assume that the Markov chain with states 1 to k and transition probabilities Pij is irreducible. Then it can be shown that all solutions lambda j is equal to 1 to k of equations are of the form as shown, where alpha is a scalar and lambda bar j is equal to 1 to k is a particular solution with lambda bar j greater than 0 for all j. Thus, the true arrival rates are given by lambda j of M is equal to alpha of M into lambda bar j. J is equal to 1 to k, where alpha of M is the constant of proportionality corresponding to M. Both alpha of M and the true total arrival rates lambda I of M increase with M. In the case where the queue service rates mu j are independent of the number of customers, alpha of M tends asymptotically to the value that makes the maximum utilization factor maximum of lambda 1 of M divided by mu M to lambda k of M divided by mu k equal to 1. Let denote Jackson's theorem for closed networks. Under the preceding assumptions, we have for all states n is equal to n1 to nk with n1 plus n2 to plus nk is equal to m, as shown. Proof. The proof is similar to the proof of Jackson's theorem for open networks. We consider state vectors n and n dash of the form as shown. Let qnn dash be the corresponding transition rate. Jackson's theorem will be proved if the rates q star nn be defined for all n dash by the equation as shown. Satisfy for all states of n the total rate equation as shown. Assume for the purpose of the proof that the particular solutions lambda bar j are taken to be equal to the true arrival rates lambda j of m, and for convenience let us denote both lambda bar j and lambda j of m as lambda j. Then we have the total rate equation is shown. We also have from these equations it is seen that the total rate equation holds good. Delay in synchronous and asynchronous time division multiplexing. Time division multiplexing (TDM) techniques is the most common transport technology used. TDM can be used in a deterministic way, which means dedicated bandwidth and dedicated delay, synchronous TDM, or in a statistical manner, shared bandwidth and variable delay, asynchronous TDM. Deterministic TDM has constant delay and bandwidth for a given individual communication channel and is used in techniques like ISDN, PDH, and SDH. Statistical TDM has variable delay and bandwidth for a given individual communication channel and is used in technologies like XC25, frame relay, ATM, or IP. MG1 queues. The MG1 system. Consider a single server queuing system where customers arrive according to a Poisson process with rate A, but the customer service times have a general distribution, not necessarily exponential, as in the MM1 system. Suppose that customers are served in the order they arrive and that xi is the service time of the ith arrival. Assume that the random variables x1, x2, so on are identically distributed, mutually independent, and independent of the inter-arrival times. Let x bar is equal to E of x is equal to 1 by mu is equal to average service time. Let x square bar is equal to E of x square is equal to second moment of the service time. Our objective is to derive and understand the Polozes-Khinchin pk formula. W is equal to lambda x square bar divided by 2 into 1 minus rho, where W is the expected customer waiting time in queue and P is equal to lambda by mu is equal to lambda x bar. Given the pk formula, the total waiting time in queue and in service is T is equal to x bar plus lambda x square bar divided by 2 into 1 minus rho. Applying Little's formula to wand T, we get the expected number of customers in the queue NQ and expected number in the system N. NQ is equal to lambda square x square bar divided by 2 into 1 minus rho. N is equal to rho plus lambda square x square bar divided by 2 into 1 minus rho. For example, when service times are exponentially distributed as in the MM1 system, we have x square bar is equal to 2 by mu square and the pk formula reduces to the equation W is equal to rho by mu into 1 minus rho MM1. When service times are identical for all customers, the MD1 system, where D means deterministic, we have x square bar is equal to 1 by mu square and W is equal to rho by 2 mu into 1 minus rho MD1. Since the MD1 case yields the minimum possible value of x bar square for a given mu, it follows that the values of W, T, NQ and N for an MD1 queue are lower bounds to the corresponding quantities for an MG1 queue of the same lambda and mu. It is interesting to note that W and NQ for the MD1 queue are exactly one half their values for the MM1 queue of the same lambda and mu. The values of T and N for MD1, on the other hand, range from the same as MM1 for small p to one half of MM1 as p approaches 1. The reason is that the expected service time is the same in the two cases, and for p small, most of the waiting occurs in service, whereas for p large, most of the waiting occurs in the queue. We provide a proof of the Polozhesk-Khinchin formula based on the concept of the mean residual service time. This same concept will prove useful in a number of subsequent developments. One example is MG1 queues with priorities. Another is reservation systems where part of the service time is occupied with sending packets, that is, serving customers, and part with sending control information or making reservations for sending the packets. Denote WI waiting time in queue of the ith customer, RI residual service time seen by the ith customer. By this we mean that if customer J is already being served when I arrives, RI is the remaining time until customer J's service time is completed. If no customer is in service, that is, the system is empty when I arrives, then RI is 0. Xi is equal to service time of the ith customer. Ni is equal to number of customers found waiting in queue by the ith customer upon arrival. We have Wi is equal to Ri plus summation j is equal to I minus Ni to I minus 1 xj. By taking expectations and using the independence of the random variables Ni and xi minus 1 to xi minus Ni, we have E of Wi is equal to E of Ri plus E of summation j is equal to I minus Ni to I minus 1 E of xj nj is equal to E of Ri plus x bar E of Ni. Taking the limit as I tends to infinity, we obtain W is equal to R plus 1 by mu nq, where R is equal to mean residual time defined as R is equal to limit I tends to infinity E of Ri. In this equation, all long-term average quantities should be viewed as limits when time or customer index increases to infinity. Thus, W, R and NQ are limits as I tends to infinity of the average waiting time, residual time and number found in queue respectively, corresponding to the ith customer. Assume that these limits exist, and this is true of almost all systems of interest to us provided that lambda less than mu. In the waiting time equation, the average number in Q NQ and the mean residual time R, as seen by an arriving customer, are also equal to the average number in Q and mean residual time seen by an outside observer at a random time. This is due to the Poisson character of the arrival process, which implies that the occupancy distribution upon arrival is typical. By Little's theorem, we have NQ is equal to lambda W, and by substitution in the waiting time formula, we obtain W is equal to R plus rho W, where P is equal to lambda by mu is the utilization factor. So finally W is equal to R by 1 minus rho. We can calculate R by a graphical argument. In below figure, we plot the residual service time RT, that is, the remaining time for completion of the customer in service at time t as a function of t. Note that when a new service of duration x begins, R of t starts at x and decays linearly for x time units. Consider a time t for which R of t is equal to 0. The time average of R of t in the interval close limit 0 to t is 1 by t integral 0 to t R tau d tau is equal to 1 by t summation I is equal to 1 to m of t 1 by 2 xi square, where m of t is the number of service completions within the closed limit 0 to t and xi is the service time of the ith customer. We can also write this equation as 1 by t integral 0 to t R tau d tau is equal to 1 by 2 m of t by t summation I is equal to 1 to m of t xi square divided by m of t. And assuming the limits below exist, we obtain limit t tends to infinity 1 by t integral 0 to t R tau d tau is equal to 1 by 2 limit t tends to infinity m of t by t into limit t tends to infinity summation I is equal to 1 to m of t xi square divided by m of t. The two limits on the right are the time averages of the departure rate, which equals the arrival rate, and the second moment of the service time respectively, while the limit on the left is the time average of the residual time. Assuming that time averages can be replaced by ensemble averages, we obtain R is equal to 1 by 2 lambda x square bar. Substituting this value in the pk formula, we get W is equal to R by 1 minus rho. This derivation is based on two assumptions: the existence of the steady state averages W, R and NQ, the equality with probability 1 of the long-term time averages with the corresponding ensemble averages. One curious feature of the pk formula is that an mg1q can have p less than 1 but infinite W if the second moment x square bar is mu. What is happening in this case is that a small fraction of customers have incredibly long service times. When one of these customers is served, an incredible number of arrivals are quenched and delayed by a significant fraction of that long service time. Thus, the contribution to W is proportional to the square of the service time, leading to an infinite W if x square bar is infinite. The derivation of the pk formula above assumed that customers were served in order of arrival, that is, that the number of customers served between the ith arrival and service is just the number in the queue at the ith arrival. It turns out, however, that this formula is valid for any order of servicing customers as long as the order is determined independently of the required service time. To see this, suppose that the ith and jth customers are both in the queue and that they exchange places. The expected queuing time of the customer I over the service times of the customers in the queue will then be exchanged with that of the customer J, but the average over all customers is unchanged. Since any service order can be considered as a sequence of reversals in queue position, the pk formula remains valid. To see why the pk formula is invalid if the service order can depend on service time, consider a queue with two customers requiring 10 and 1 units of service time respectively. Assuming that the server becomes available at time 0, serving the first customer first results in one customer starting service at time 0 and the other at time 10. Serving the second customer first results in one customer starting at time 0 and the other at time 1. Thus, the average queuing time over the two customers is 5 in the first case and 0.5 in the second case. Clearly, queuing time is reduced by serving customers with small service time first. For this situation, the derivation of the pk formula breaks down since the customers that will be served before a newly arriving customer no longer have a mean service time equal to 1 by mu. MG1 queues with vacations. Suppose that at the end of each busy period, the server goes on vacation for some random interval of time. Thus, a new arrival to an ideal system, rather than going into service immediately, waits for the end of the vacation period as shown in figure. If the system is still idle at the completion of a vacation, a new vacation starts immediately. For data networks, vacations correspond to the transmission of various kinds of control and record-keeping packets when there is a lull in the data traffic. Other applications will become apparent later. Let V1, V2 be the durations of the successive vacations taken by the server. We assume that V1, V2 are independent and identically distributed IID random variables, also independent of the customer inter-arrival times and service times. As before, the arrivals are Poisson and the service times are IID with a general distribution. A new arrival to the system has to wait in the queue for the completion of the current service or vacation and then for the service of all the customers waiting before it. Thus, the waiting time formula W is equal to R by 1 minus P is still valid, where now R is the mean residual time for completion of the service or vacation in process when the ith customer arrives. Network of queues, Jackson's theorem. Definition. The main difficulty with the analysis of networks of transmission lines is that the packet inter-arrival times after traversing the first queue are correlated with their lengths. It turns out that if somehow this correlation were eliminated and randomization is used to divide traffic among different routes, then the average number of packets in the system can be derived as if each queue in the network were MM1. This result is known as Jackson's theorem. Derivation. Consider a network of k first come first serve single server queues in which customers arrive from outside the network at each queue I in accordance with independent Poisson processes at rate Ri. We allow the possibility that Ri is equal to 0, in which case there are no external arrivals at Qi, but we require that Ri greater than 0 for at least one I. Once a customer is served at Qi, it proceeds to join each Qj with probability Pij. The routing probabilities Pij together with the external input rates Rj can be used to determine the total arrival rate of customers lambda j at each Qj. Calculating lambda j is fairly easy when the network is of the acyclic type. If there is a positive probability that a customer may visit the same queue twice, a more complex commutation is necessary based on the equations. Lambda j is equal to Rj plus sigma I is equal to 1 to k lambda I Pij, j is equal to 1 to k. These equations represent a linear system in which the rates lambda j is equal to 1 to k constitute a set of k unknowns. To guarantee that they can be solved uniquely to yield lambda j is equal to 1 to k in terms of Rj Pij I j equal to 1 to k, we make a fairly natural assumption that essentially asserts that each customer will eventually exit the system with probability 1. The service times of customers at the jth queue are assumed exponentially distributed with mean 1 by mu I and are assumed mutually independent and independent of the arrival process at the queue. The utilization factor of each queue is denoted rho j is equal to lambda j by mu j is equal to 1 to k. We assume that Pj less than 1 for all j. It is necessary to accept several simplifying conditions in addition to assuming Poisson arrivals and exponentially distributed packet lengths. The independence of packet lengths and inter-arrival times. The assumption that bifurcation of traffic at a network node can be modeled reasonably well by a randomization process whereby each departing packet from Qi joins Qj with probability Pij, this need not be true. Still, a packet network differs from the model of this section because it involves several traffic streams which may have different routing probabilities at each node and which maintain their identity as they travel along different routes. This difficulty can be partially addressed by using an extension of Jackson's theorem that applies to a network with multiple classes of customers. Within this more general framework, we can model traffic streams corresponding to different origin-destination pairs as different classes of customers. If all traffic streams have the same average packet length, it turns out that Jackson's theorem, as stated below, is valid assuming the simplifying conditions mentioned. For an analysis, we view the system as a continuous time Markov chain in which the state n is the vector n1, n2 to nk, where ni denotes the number of customers at qi. At a given state, n is equal to n1, n2 to nk. The possible successor states correspond to a single customer arrival and or departure. In particular, the transition from n to state nj plus is equal to n1 to nj minus 1, nj plus 1, nj plus 1 to nk. Corresponding to an external arrival at qj has the transition rate qnnj plus is equal to rj. The transition from n to state n of j minus is equal to n1, nj minus 1, nj minus 1, nj plus 1 to nk. Corresponding to a departure from qj to the outside has transition rate qnnj minus is equal to mu j into 1 minus sigma I pji. The transition from n to state ni plus j minus is equal to n1, ni minus 1, ni plus 1, ni plus 1, nj minus 1, nj minus 1, nj plus 1, nk. Corresponding to a customer moving from qj to qi has transition rate qnn I plus j minus is equal to mu j pji. Let p of n to nk denote the stationary distribution of the chain. We have Jackson's theorem. Assuming that pj less than 1, j is equal to 1 to k, we have for all n1 to nk greater than or equal to 0, p of n is equal to p1 of n1, p2 of n2 to pk of nk, where n is equal to n1 to nk and pj of nj is equal to rho j power nj into 1 minus rho j, nj greater than or equal to 0. Proof. Assume that lambda j greater than 0 for all j. There is no loss of generality in doing so because every qj with lambda j is equal to 0 is empty in steady state. So we have pj of 0 is equal to 1 and pj of nj is equal to 0 for nj greater than 0, and qj can be ignored in deriving the stationary distribution. It can be verified that the condition lambda j greater than 0 for all j together with the assumption made imply that the Markov chain with the states n is equal to n1 to nk describing the system is irreducible. For any two state vectors n and n dash, let qnn dash be the corresponding transition rate. Jackson's theorem will be proved if the rates qnn star defined for all n dash by the equation q star nn dash is equal to p of n dash q n dash n by p of n satisfy for all n the total rate equation sigma m q nm is equal to sigma m q star nm is equivalent to the global balance equations. For transitions between states n, nj plus and nj minus, we have qnnj plus is equal to rj. qnnj minus is equal to mu j into 1 minus sigma I pji. using the fact P of nj plus is equal to rho j into P of n is equal to lambda j into P of n divided by mu j, we obtain Q star nnj plus is equal to lambda j into 1 minus sigma I pji. Q star nnj minus is equal to mu j rj divided by lambda j. Next, consider transitions between states n and ni plus j minus corresponding to a customer moving from qj to qi. We have qnni plus j minus is equal to mu j into pji, and using the fact that P of ni plus j minus is equal to rho I into P of n divided by rho j is equal to lambda I mu j into P of n divided by lambda j mu I. We obtain Q star n I plus j minus n is equal to mu I lambda j into pji, the whole divided by lambda I. Since for all other types of pairs of state vectors n dash we have q n dash is equal to 0, it follows that q star n dash n is equal to 0. There remains to verify that the rates qnm and q star nm satisfy the total rate equation we have for the forward system equation as shown. Similarly, we obtain for the reversed system as shown. By writing lambda j is equal to rj plus sigma I is equal to 1 to k lambda I pij, j is equal to 1 to k, as rj is equal to lambda j minus sigma I is equal to 1 to k lambda I pij, and adding over j is equal to 1 to k, we obtain sigma j is equal to 1 to k rj is equal to sigma j is equal to 1 to k lambda j into 1 minus sigma I is equal to 1 to k pji. From these equations, we see that sigma m q nm is equal to sigma m q star nm is satisfied. Jackson's theorem says in effect that the number of customers in the system's queues are distributed as if each queue is m1 and is independent of the other queues. Despite this fact, the total arrival process at each queue need not be Poisson. Shown in figure is an example of a queue within a network where the external arrival process is Poisson, but the total arrival process at the queue is not Poisson. An external arrival is typically processed fast and with high probability returns to the queue through the feedback loop. As a result, the total queue arrival process typically consists of bursts of arrivals, with each burst triggered by the arrival of a single customer from the outside. Heuristic explanation of Jackson's theorem. Suppose that we introduce a delay delta in the feedback loop of the single queue network discussed previously. Let us denote by n of t the number in the queue at time t, and by f delta t the content of the delay line at time t. F delta of t is a function of time that specifies the customer output of the delay line in the subsequent delta interval t plus delta. Suppose that the initial distribution n of 0 of the Q state at time 0 is equal to the steady state distribution of an MM1Q, that is, P of n of 0 is equal to n is equal to rho power n into 1 minus rho, where P is equal to lambda by mu into 1 minus P is the utilization factor. Suppose also that F delta of 0 is a portion of a Poisson arrival process with rate lambda. The customers in F delta 0 have service times that are independent, exponentially distributed with a parameter mu. Assume that n of 0 and F delta of 0 are independent. Then the input to the Q over the interval 0 to delta will be the sum of two independent Poisson streams which are independent of the number in the Q at time 0. It follows that the Q will behave in the interval 0 to delta like an MM1Q in equilibrium. For all t which are multiples of delta, n of t and f delta of t have the same properties. Extension of Jackson's theorem. A few extensions to the Jackson's theorem are Jackson's theorem for state-dependent service rates, multiple classes of customers. State-dependent service rate. An extension to the multi-server case can be obtained by allowing the service rate at each queue to depend on the number of customers at that queue. Thus, the model is the same as before, but the service time at the jth queue is exponentially distributed with mean 1 by mu I of m, where m is the number of customers in the jth queue just before the customer's departure. The single queue version of this model includes as special cases the MMM and MM infinity queues and can be analyzed by means of a Markov chain. The corresponding network of queues model can also be analyzed by means of a Markov chain and is characterized by a product form structure for the stationary distribution. Rho j of m is equal to lambda j by mu j of m. J is equal to 1 to k, m is equal to 1 to, where lambda I is the total arrival rate at the jth queue. P cap j of nj is equal to 1 if nj is equal to 0, rho j of 1, rho j of 2 to rho j of nj if nj greater than 0. Jackson's theorem for state-dependent service rates. We have for all states n is equal to n1 to nk. P of n is equal to p cap 1 of n1 to p cap k of nk by g, assuming that 0 less than g less than infinity, where the normalizing constant g is given by g is equal to sigma n1 is equal to 0 to infinity to sigma nk is equal to 0 to infinity of p1 cap of n1 to pk cap of nk. Proof. The formula for G guarantees that P of n is a probability distribution, that is, the sum of all P of n is unity. Using this fact, the proof is obtained by repeating the steps of the earlier proof of Jackson's theorem, substituting the state-dependent service rates mu I of m in place of the rates mu I at the appropriate points. Multiple classes of customers. Let the customer classes be C is equal to 1, 2 to C. Let RIC be the rate of the external Poisson arrival process of class C at Qj, and let Pij of C be the routing probabilities of class C. The assumptions made for an open Jackson network with a single customer class are replicated for each customer class so that the equations lambda j of C is equal to Rj of C plus sigma I is equal to 1 to k lambda I of C Pij of C. J is equal to 1 to k, C is equal to 1 to can be solved uniquely to give the total arrival rate lambda j of C at each Qj and for each customer class C. Assume that the service times at Qj are exponentially distributed with a common mean 1 by mu I of m for all customer classes, which depends on m. The total number of customers in Q. Customers are served on a first-come, first-served basis. The state of each queue is characterized not just by the total number of customers present in the queue, but also by the class of customers and the relative order of arrival of the customers of different classes. Thus, the composition of the jth queue at a given time as Zj is equal to C1, C2 to Cnj, when Nj is not the total number of customers in the queue and Ci is the class of the customer in the ith queue position. The state of the queuing network at a given time is Z is equal to Z1, Z2 to Zk, where Zj is the composition of the jth queue at the given time. It can be viewed as the state of a Markov chain, the transition probabilities of which can be described in terms of the given quantities lambda j of C, mu j of m, and Pij of C. To state the appropriate form of Jackson's theorem, define P cap j of C, m is equal to lambda j of C by mu j of m. J is equal to 1 to k, C is equal to 1 to C. P cap j of Zj is equal to 1 if Nj is equal to 0. N cap j of C1, 1 into P cap j of C2, 2 to P cap j of Cnj, Nj if Nj greater than 0. G is equal to sigma Z1 to Zk pi j is equal to 1 to k P cap j of Zj. Jackson's theorem for multiple classes of customers. Assuming that 0 less than g less than infinity, the steady state probability P cap of Z of the state Z is equal to Z1, Z2 to Zk is given by the steady state probability P of n is equal to P of n1 to nk of having a total of nj customers at Q. J is equal to 1 to k irrespective of class is given by where Z of n is the set of states for which there is a total number of ni customers in Qj. When the service rate at each queue is the same for all customer classes and is independent of the queue size, we have P of n is equal to pi j is equal to 1 to k rho j power nj into 1 minus rho j, where rho j is equal to sigma c is equal to 1 to c lambda j of c divided by mu j, and mu I is the service rate at Qj. Queuing systems MMSK queues. Characteristics. Inter-arrival time is exponential with rate lambda. Arrival process is Poisson process with rate lambda. Inter-arrival time is exponential with rate mu. Number of services is Poisson process with rate mu. Multiple server. Number of servers is equal to S. Independent servers. Parallel service channels. Identical servers. Random choice of idle servers. System size is finite. Total number in system less than or equal to k. Q discipline FCFS. Notation M/M/S/K/FCFS. Steady state distribution. State of the system. System is in state n if there are n customers in the system waiting or serviced. Let Pn be the probability that there are n customers in the system in the steady state. N is equal to 0, 1, 2, 3, k. Rate diagram. Consider an MM3K system. System in state n is equal to 1 implies one server busy implies total service speed is equal to mu. System in state n is equal to 2 implies two servers busy implies total service speed is equal to 2 mu. System in state n is equal to 3 implies 3 servers busy implies total service speed is equal to 3 mu. System in state n is equal to 4 implies 3 servers busy implies total service speed is equal to 3 mu. System in state n greater than 3 implies 3 servers busy implies total service speed is equal to 3 mu. As shown. Rate diagram. Arrival rate is equal to lambda for all states of the system. Service rate is equal to n mu if n less than or equal to s. Service rate is equal to s mu if s less than n less than or equal to k. Pn is a function of p0 if p0 is equal to 0. System is infinite. System is finite if and only if p0 greater than 0. Computing p0 as shown. Pn formula as shown. Performance measures. Blocking probability BP. BP equal to PR, system is full, is equal to PK. Effective arrival rate lambda E. Lambda E is equal to arrival rate dot PR, system is not full, is equal to lambda dot PR n less than k is equal to lambda dot 1 minus BP is equal to lambda dot 1 minus PK. Average customers in system LS equation as shown in average busy servers LB as shown. LB is equal to E busy servers is equal to E into hash cust in service. Using Little's formula, LB is equal to lambda E WB. WB is equal to average time server is busy is equal to expected service is equal to ES is equal to 1 by mu. LB is equal to lambda E WB is equal to lambda E by mu. Average customer in Q LQ as shown. Utilization of the system U. U is equal to PR n greater than 0 is equal to P1 plus P2 plus P3 so on up till Pk is equal to 1 minus P0. Utilization of the service SU. SU is equal to PR, all servers busy, is equal to PR, N greater than or equal to S. SU is equal to 1 minus P0 plus P1 plus P2 so on up till Ps minus 1. Average time spent in system WS. LS is equal to lambda E WS. Double implies WS is equal to LS by lambda E. Average waiting time in queue WQ. LQ is equal to lambda E WQ. Double implies WQ is equal to LQ by lambda E. Conclusion. In this chapter, we have covered the following in detail. Queuing systems MMSK queues, Burke's theorem, MG1 queues, delay in synchronous and asynchronous time division multiplexing, network of queues, Jackson's theorem, closed queuing networks.